Hi, everybody. Kind of fun to be at UEC since I've been here for over 20 years before. The room where we had faculty meetings, so kind of interesting to be back. Right now, I'm actually talking much more from the viewpoint of Intrinsic, which is actually an independent alphabet company, or it's Google. And I'll tell you a little bit our view towards benchmarking and how this might look like in the future. So just some motivation, okay? In general, I have to stay close to the microphone. It is super interesting to see what's happening in robotics and what happens in research and what prototypes exist. The question is actually how to get them to something which actually works. And there is a huge divide until you get there. There's lots of what works in a video is great, and many of you have seen most likely very deceptive videos in the last year. And if you then look at what's behind it, this is nowhere close to what is really reasonable performance. And so we are super interested in getting actually a research ecosystem connected to an ecosystem which is really applicable to real-world applications. I can't help, given that I've been teaching here Introduction to Robotics for 20 years, I like to emphasize that robotics is about physics. And many people sometimes forget that physics is not very nice and not very forgiving. And we want to put now increasingly more AI into the control loops and make these things work. And there's one thing which will not work. If you shoot stuff at the robot which is non-physical, they just do very terrible behavior. No fun at all. Just as a reminder, I know it's a robotics conference, but I can't help. So in the more practical world, people have all these kind of technology readiness levels, which is a common way of expressing how far you have gotten. And it starts with 1, which is basically more conceptual phases. Everything which is red is mostly conceptual. Then light blue is becoming more prototypes, which are usually at research labs, university labs, etc. If you make the step to level 7, then you start to be actually having something which might actually work. But people want level 9. They want something which really, really works. And it's a very big step to go from the blue field to the purple field. And the interesting thing is there's beautiful learning curves out in the machine learning community for robotics, okay? And they do one thing in common, they usually go up unless it's a disaster. But what the hell does it mean, the mean reward on the left side, and what does it mean in practical performance? And my general complaint is that, okay, most performance success rates are like 60, 70, 80%. Sometimes you see 90, which is really nice, maybe on a very simple task. And yeah, this is cool, machine learning, optimization. In machine learning in general, if you can do cancer detection with 90% probability, you will be famous. It will be fantastic. If you're a human being, and when you stand up out of your chair, and 1 out of 10 times you fall flat on your face, Darwin will take care of you. You'll be out. So the requirements on reliability in physical systems is super different than in kind of statistical machine learning. And it's just interesting to keep this in mind. So what's happening in the world? All of you are aware of this. AI, generative AI, makes a huge difference and basically propels all kinds of fields in crazy ways. Whether it's realistic occasionally, we can talk about this, but it's moving forward. Hardware is also making a huge amount of steps forward. Look at what Jensen has been presenting in the last NVIDIA conference in terms of what new hardware will come out. Google is having their TPUs, and there's new sensors and all kinds of things coming out, which actually enable that you can do in robotics things which are really cool. I think one of actually the big events in robotics at some point was actually the Kinect sensor for Microsoft, where the first time you could do 3D vision without having a crazy vision pipeline which you had to program yourself. Made a huge difference, and so there's lots of new machine learning. From the viewpoint of kind of intrinsic, there's also one other very big component. These are general robotics platforms. And I think ROS is something everybody knows, and maybe you know that ROS is actually part of Intrinsic by now. So we are actually working together on basically creating an even more capable platform for robotics, which is basically providing software to any robot, complete hardware abstraction, always the same interface, lots of things that Adam actually mentioned is actually going to be realized in this platform, except that it's maybe not quite ready yet for prime time usage. So that's kind of exciting. So let's get to benchmarking. And I think Adam already mentioned a lot of these points. So in order to basically create a robotic system that does something, you need to address so many different things. Control theory, physics, real-time computing, the robot hardware in particular, then perception, vision, tactile, whatever perception you want. Machine learning comes in various flavors, in various kind of programming languages, and yeah, implementation details. Software engineering to really make the system work as a whole, not that it gets like the good old ROS1 completely congested and all the message passing that was going on. And you need to also integrate this all together and make it work. What is that little message? That's not me, okay. And in the end, how you put this system together, and this is also what Adam mentioned, makes a huge difference whether the whole system will work. And one component may actually be the one which causes your bad performance, but it may not be the one which you're focusing on. And it's a huge amount. This is just, I've been doing robotics labs for so many years. Putting together the systems, maintaining them, making them work, and also taking care that your robot doesn't sound weird. That means there's some too much friction, or that's why the thing is basically getting into wear and tear problems, is a pain. So what would help? And I think, Adam, you mentioned that already. So standardized robotic software, standardized platforms, suitable abstraction. Every robot should not look different and have a different interface. It should all look the same. Actually, this is what industry wants. Exactly the same as we would love in research. They just go to big car manufacturers. They have, I don't know how many different robot brands. For everybody, they have to basically train up a couple of experts who maintain them, who understand their software, their programming languages, their idiosyncrasies, and God knows what's going on. And they would love that this all goes. Oops, sorry. Microphone. Standardized data collection. Everybody who's worked in kind of ML-based robotics, data collection is a pain. Whatever, how big are the images you can pipe through, how to get the data at which kilohertz rate or whatsoever. Actually, fun things, okay? If you just collect data at 10 hertz and you have a force torque sensor, you're missing about 99% of the data. So that's also a very bad idea how to collect data. You want standardized evaluations at some point. You want someone who maintains the hardware really well. And this is actually fun. I was part of RTX, as among other 100 people, God knows what. Just getting someone evaluate software on some arbitrary lab-maintained robot. How can you trust that? They maintain these things in the most pathetic way. You don't even know whether they're calibrated. So complicated, let's put it this way. And you would love to have modularized systems, of course, so that you can easily test the components you want. Again, Adam mentioned that very nicely. Ideally, you want remote control, monitoring of performance, and ease of use. This is a nice laundry list, huh? So just a question how you basically realize that. So let me tell you a little bit what we've been doing, and also what's happening in the bigger Google empire, I would say. So this general robotics platform is super close to our heart. And this is a little bit of a PR video, which we have on the Intrinsic web page. This is kind of a web-based front end, which allows you to connect to your robots in simulation or in real physical systems. It gives you some visualization, digital twin, if you want to call it this way. You have behavior trees, how to basically create kind of sequence behaviors. You can actually put work cells together from parts that are already being put into the system. You can work with Franka robots, UR robots, EVA robots, KUKA EVAs. You can work with lots of different cameras. You can calibrate them automatically. You get everything through the web, and it's all kind of containerized, Kubernetes-based. It's a very modern way of doing ROS, to be quite honest. Much more professional software engineering, but also not as open source, unfortunately. So that's kind of the disadvantage. And also one component which we have worked on with a fairly big perception group over time is really to make it easy to basically do at least rigid body pose estimators. And all what you need initially is a CAD model, and then you upload that through a front end. You have to provide a little bit of additional information, and You can calibrate your cameras. You can basically create deep learning pose estimators with various really good techniques. You can work with various cameras, whatever you want. And you get within either minutes or at the worst hours a very performant pose estimator, which is really robust to lighting conditions and whatsoever. And this is actually, this kind of ease of perception is something which we use in benchmarking. Since I'm coming to this in a second, when we try to create automated benchmarks, we have to take some advantages of stuff that works. Like for instance, pose estimation. Even if I don't want to use pose estimation in the traditional way in my robotics applications, I can nevertheless create data in this way, and I can also evaluate by using those abilities. Keep going. Data. Okay, data is a pain, and everything goes into data-driven robotics, despite I would actually argue that please use anything you know about real-time robotics, about traditional perception, about traditional machine learning. Don't throw away all that beautiful knowledge built on top of your machine learning. Do not try to exclude it. This makes no sense at all. You will never get to really performant robots unless you use the best of everything. But when it comes to data, okay, the current paradigm is obviously people like human data collection with kind of teleoperation. This is a data pyramid. This is totally cool.
I should actually, if you wanted to have it scaled to how much data is visible in this thing, it would be the internet scale at the bottom, and there would be a needle.
Since there is no data, this is just completely ridiculous. So the human data collection is terribly slow. We are collecting data in automatic, kind of what we call scripted data collection, which at least gives us about 100 times to 1,000 times more data, which is still not numbers, but the internet is in NVIDIA, there's a lot of simulation. I think there's a massive amount of work there. This can create a lot of data, and then of course, YouTube videos, internet scale would be massive, but nobody has actually made real good use of that. The fun thing, what we can do, at least in our intrinsic platform, is we can create automatic data collection.
Since the thing is perfectly structured and it's standardized,
and that means every component collects its own data, logs it into the cloud, makes it available at whatever frequency you want. So we call this a data engine. Again, this is all still in a research state. It's coming together, it's working, and we are using this to train models, but it's not performant and working well enough all the time. But in some sense, the data engine was popularized at least by Tesla. That's what they do with their cars. And in some sense, we would love to do something similar with kind of the intrinsic platform. And that would be a platform that would be generally used. You would actually get a lot of data. It doesn't say that the data is good. So you gotta be careful. You have industrial robots and just a spot weld, and here after 1 hour you don't get any new data. It's always the same data. Nothing changes. So that's not the data you want. But maybe if you get this from 2,000 spot welding cells, becomes interesting again. Some examples of what we've been doing in the past to basically benchmark what we've been doing. We've been creating, this was actually the DeepMind London at some point, the robotics group over there, where we created this generic kind of something called a cable monster, a connected insertion setup where the robot could just basically test and see how well it's doing this, and you can actually instrument that, you could actually get signals whether it was successful or not. Success classifiers are actually also an interestingly complicated topic. How do you actually know that you did the right thing? How do you get the metrics and everything they mentioned there? Not so much fun. Keep going. This is actually just benchmarking the pose estimator. The system has a generic pose estimator for these nodes, which we're using actually as nests to put the electronics parts inside, so you see where they are and then manipulate them afterwards. And it just do this around. It's nice. It's actually a very important system. It's easy with 99.99%. Not bad for fragments. But that's also not good enough, since if I want to basically do automatic data collection, then 99.99% still means that I usually have it down once or twice a day. This is actually fun. This was actually the bin-picking challenge, perception challenge for bin-picking, the official word, which was actually just finished right now. It was part of the CVPR. It was also funded, supported by OpenCV. And this was basically that we created from an intrinsic point of view a work cell which had all the ingredients and such the robot moves, and people just had to upload
their particular perception and bin picking solution in a containerized way. And then they could test it on our work cell remotely, so they didn't have to touch anything. They could also do it initially in simulation. You see on the right side actually the interface to the system, on the left side is the real system. And that just came to a conclusion, and there's some winners of that. But it was the first time that we actually exercised that people could use that system for benchmarking and evaluations from the external point of view.
And there's lots of other examples, of course, about what people do for benchmarking, data collection. Top left, I think, is Tesla. On the top right, this is actually done by DeepMind Robotics, a dual-arm Franca work cell. They have lots of them. They just duplicated them such they have within their own company or their own team some reliable benchmarking and repeatability. Of course, this is not available to the people outside. This is the ARM on the left side, which was at Google X long time ago, together with Brain Robotics, the old name, and Aloha setups, which are all over the place, including physical intelligence, Google, and others, of course, which are super popular. So let me come to the end of this. We are interested in automatic evaluations, so we don't have to do this with humans anymore, but they only work on certain tasks. So t-shirt folding and stuff like that is most likely not part of that. You need automatic resets. You need to basically be able to use other technology to create the data such that then you can evaluate with a machine learning model. Hopefully gets better than what you originally put in. Someone has to maintain these robots. And the question is, who wants to do this? This is almost something which needs to be outsourced to someone who really puts full focus on creating these work cells and making them available to the community. Ideally, some place like Interoperability should be doing that. We don't have the headcount. We would love to do it. It would be absolutely the right thing to do. And we do it in some, in the perception bin picking challenge, we did it at least in a particular example, but doing this on a bigger scale requires a lot of people. And most likely you don't want to go to Silicon Valley. It's expensive. You need all the software infrastructure to maintain and make it work properly so that people can focus on the individual modules. Now this is beautiful in the platform. So for instance, motion planning, what you mentioned before, Adam, perception is done. All kinds of real-time control, whatever operational space controllers or joint space controllers, whether it's a position robot or a truck robot, it's all exists. Unfortunately, it doesn't exist so far for the general public. So we hope to roll out what we call flow state research in about a year from now. And then software tells you, I'll do it in 1 year, then multiply it by 2. You never know. This is most realistic. Ideally, everything should work in sim and real. You have sim. It works, but it's not contact proven. So it is not good enough for real contact with simulation. But contact is for everybody a huge problem, I would argue. Yeah, and ideally what I mentioned, there should be benchmarking farms accessible to everybody, since that would actually make a huge difference. It may not be the only thing to do, but it would be really nice if there would be whatever 100 robots or so out there that people could just upload their things and someone else takes care of the maintenance of the robots, and also make sure the entire system is safe, that it only focuses on what you want to test and not destroy anything else. All right, and that is coming to the end. Thank you very much.
Questions?
Yes.
Stefan, while you focused on benchmarking, you also were in support of modularity,
yes.
The way I understood it, which is not necessarily a trend on on popular solutions these days, right?
It's a long discussion. So the way we're looking at this, so interesting to do these kind of behavior trees is very structured and very old-fashioned state machines that we want. So, and ideally, what people want, they want just a state machine with one block, which is my general end-to-end universal policy. And we're happy to do all of this. All of this can be realized, except if you want to go to the level that you can test some modules like a bin-picking component or a whatever manipulation component or an error algorithm, then you could insert it here and just use all the other infrastructure to basically not worry about it. But I fully agree. If you just want a complete system end-to-end solution, then
that would be doable as well. It's just I would not do it this way, to be honest. This is just also from a data generation point of view. If you want to get enough data, you need to create more solutions with robotics which work. And then even if they're handcrafted, they create data. And then hopefully you feed this into your bigger models, which get increasingly better at end-to-end learning, and actually become maybe the generalist at some point. But it's a tricky question what to do first. I can give you more information there, but I think it's getting too long.
So maybe a follow-up from that one. We talk a lot about standardization, and we really want that. But when you go to industry, you deal with the lines after the comma, right? And a lot of that comes from uncertainty. Certain things that you have modeled, but are not exactly as you modeled. So how do you see that interplay between standardizing a lot of interfaces and tests versus leaving that uncertainty?
For the standardization, this gives you modules which you can rely on. How you put them together doesn't really matter. If you have uncertainty, you still you basically have you just do the standard, like you don't need to learn free space motion, right? I can never say that. Okay, this is kind of the most irrelevant thing to do in the universe. But I don't know how to do contact manipulation. So we do free space motion, the standard, whatever behavior tree, and then comes whatever the RL law, which uses a policy which has been trained in a completely different way, and it's then used there, and it can deal with the uncertainty or whatever, which I don't understand. But we try to basically wiggle our way through using as much prior knowledge as possible. Again, it's always possible to throw it all away at some point. But okay, you will not survive at least in this kind of startup world in the world.
My interpretation of the question is more about how do we deal with the uncertainties of the real world and model that in a way such that we can actually measure what the real world tell what happens in the real world.
I guess there's a philosophical question, right? Like around uncertainty, where does it come from? How does it work?
Certain things are uncertain about just trying to very tight connectors. It's a nightmare. All the electronics parts are different. They're not really well manufactured. It's not like cars, which is sub-millimeter super precision. So it's an interesting question. Yeah. I just know how to look at the question. Yes.
I do agree with you about the data the pyramid that you're showing, more of internet scale data. From your personal point of view as well as intrinsic point of view, what is it that needs to be done to get good data?
To get data?
Good data, yeah.
Good data. Right? So, fine. Our answer so far has been that we tried, and this is again a small spectrum of tasks, we tried to use scripted motion generation to use all our robotics knowledge to get good data, and we create enough variability in this data which we can do artificially, including motion injection if you feel this is important to do, and make sure you get coloring and interesting spectrum of things. And that gives us the bulk of data, and then we would use basically a little bit like from the order of 50, 100 kind of data operation trajectories if we feel we need more data to find. So, and together with my London, we have principle for a long time that whatever reinforcement learning algorithms we've been running, they always had the possibility that users could interrupt and the operator part, because usually the mobile got stuck in its policy. And usually with this relatively few trajectories, 20, 30, we can get it out of this kind of local minimum and keep on working. So these kind of things are helpful. It just totally, just all the jittery data you get from teleoperators, and then there are different ways of doing things. It's hard to work with this data, to be honest. It's cool data. It's very hard to kind of collect, and then it's wrong, they have to throw it away. So I have lots of people next to me in DeepMind Robotics do literally this. It's an enterprise, to be honest. It's very slow, so we will never get to the whatever transformer scale of data that maybe the transformers want, or we just come up with a better model.
Right. Let's save our questions for the breakout.